Morning, everyone. I'm Haichen Shen. So today I'm going to talk about Nexus. So this is Nexus is a GPU cluster engine for accelerating DNN-based video analysis. And this is a joint work with researchers from University of Washington, Microsoft Research, and Northeastern University. In this paper, we focus on the workload of analyzing videos at large scale. This application can analyze streams of videos ranging from traffic camera, surveillance, game streaming, and family cameras. Each application can receive a few streams to as many thousands of streams. So the serving has to be done at scale. So before we talk about the serving system, let's first take a look at what happens inside a video analysis pipeline for each video stream. So it can be structured into 4 stages. So first, we can sample some frames and then perform some lightweight analysis such as motion-based filtering. And then we use neural networks to analyze the video contents, and then we aggregate the results. So the DNN-based analysis is where the most computation happens and what it costs most. So in this work, we particularly focus on how to serve this workload. So how are DNN serving system architecture today? In fact, it is not much different from the traditional distributed serving systems such as web serving. They both instantiate front-end and back-end servers for an application. They both do auto-scaling and load balancing for the scalability. And the application has certain latency constraints as the latency SO. However, there are additional constraints that are unique to the DNN workload. For example, first, because the neural networks are more computational intensive, it is common to use accelerators such as GPU in the backend in order to finish the task within the time budget. In this paper, we focus on the GPU for the accelerator, but the principle can also apply to other accelerators as well. So second, because the size of a neural net model is quite large, so it takes much longer time to load this model into memory than processing a single task. So therefore, these models need to be pre-scheduled and pre-allocated at the backend before serving them. And third, because the GPUs and accelerators are relatively more expensive, so to make it more cost-effective, we need to maximize the utilization of accelerators. And batch processing is one of the key techniques to achieve this. And existing systems such as TensorFlow serving and Clipper already address these constraints. But however, they are mostly scoped at a single application. So as they do not coordinate the resources allocation across DNN applications, and they rely on external schedulers that cannot perform cross-app optimizations. So in this paper, we're going to explore the problem of how to build a serving system that can coordinate the serving of multiple DNN applications. There are 3 main levels of optimization opportunities, starting from the cluster level to inside the application and then down to the model level. And I'm going to explain them in details in the next few slides. So let's first look at the class level resource allocation problem. So given a bunch of models with different latency SOs, how can we schedule these on the GPU cluster in order to maximize the utilization of this cluster? Let's start from a simple example. Given that suppose we have a model has a latency SO of 12 time units, and they receive 1 request every 2 time units. If we execute a batch of this model at 8 time units as our duty cycle, we then can get a batch size of 4. And because the execution of this batch size 4 takes another 4 time units, so the worst latency of a request can be up to 12 time units just within the latency SO of this model. However, if we increase the duty cycle to get larger batch size, we'll then violate this model's latency SO. Therefore, the latency SO limits the batching optimization. Now let's consider placing multiple models on the same GPU while respecting their latency SOs. So model 1 has a duty cycle of 8 time units, and they require 50% of the GPU cycles. Similarly, for model 2, we can batch 3 requests at 12 time units as the duty cycle, and also requires 50% of the GPU cycles. So at first glance, it will appear that we can co-locate these 2 models on the same GPU as they both require 50% of GPU cycles. But if we want to put them on the same GPU, we need to make sure they simultaneously meet their latency requirement. And in particular, model 1 has a more stringent latency constraints, and the model has to be invoked every 8 time units. So therefore, we need to reduce the duty cycle and invoke model 2 more often. And after we reduce the duty cycle of model 2 down to the 8 time units, the batch size also decreases to 2 requests. And smaller batch size increases per task cost, And therefore, now Model 2 requires 63% of the GPU cycles. As a result, we cannot place these two models on the same GPU while both models satisfy their latency SOs. So the challenge here is that the GPU sharing has to account for both latency SOs and the squishy load demands across models. Second, let's take a look at the application. So application can have a complex query that use multiple models and serve one request and have dependency between them. So here, this figure shows a simple example of a complex query where you first use the object detection model to detect objects from a video frame, and then you use recognition model to recognize each of the objects. And the number of objects detected from each frame can vary depending on the workload. And existing DNN serving system assume the latency SOs specified at the model level. But in many applications, it's more natural the granularity to express the latency SO is at the application level. So the question is, how can we allocate and split the latency SO of an entire pipeline to each individual model so that we can know what batch size to use for each model? So, and also, does the latency split actually affect the efficiency of the entire pipeline? So let's use this example and then consider 3 different strategies to split the latency into each models. For example, we can allocate 40 milliseconds for the detection model and 60 milliseconds for the recognition model. And after some detailed simulation on different workload, and it turns out that none of the split can get the best efficiency overall across all workloads. So we can learn 2 things from this example. First, the latency split does affect the efficiency of this complex query. And second, we need to understand the distribution of the workload and adapt this latency split to the workload. Now third, the transfer learning is a common technique used in the machine learning community that we can adapt a model to a different data set and different task. So what happens usually is that we fix the weights of bottom layers of a model and only retrain the top one or a few layers. And then we can, after we retrain the top layers on different data sets, we can get a series of new models. However, if we treat these models differently, we then lose a bunch of opportunity of the batching. So, but given the fact that these models share the common prefix, so can we speed up this part across models? So in order to address these optimization opportunities and challenges, we build a Nexus, and it uses 3 main techniques to address these challenges, and I will go through over them one by one. And let's start from the resource allocation. So the resource allocation problem has a structure of bin packing problem. So we need to pack model sessions into GPUs. Our optimization goal is to minimize total number of GPUs to serve the workload, while we need to satisfy the constraint that requests need to be served within the latency SOs. Our problem is more complicated than the classic bin packing problem because we can change the batch size of a task, and then we need to meet the latency SOs. As we all know, the bin packing problem is an NP hard problem, so we need some approximation solution to this problem as well. So we derive a heuristic algorithm called the squishy bin packing problem, which it works in 2 phases. In the first phase, we allocate 1 GPU for each model session and choose the largest batch size, such that it won't exceed its latency SO. And it also indicates that the duty cycle is the largest one we can use. And if the execution latency, the batch execution latency is smaller than the duty cycle, as shown in this figure, we then have some extra cycles so we can fit in other model execution to increase the GPU utilization. And as an analogy to the classic bin packing problem, the duty cycle can be viewed as the empty bin, and the batch execution are the balls we need to put into these bins. But the major difference is that these balls are squishy, as we can change the batch size. So in the second phase, we'll start to merge these nodes into fewer nodes. And during this process, 2 environments need to be maintained for the correctness. First, the duty cycle will never increase, as we already used the largest one in the beginning. And second, the occupancy of combined nodes should never be greater than 1. And the left question we need to address is that how should we merge 2 nodes, and then which nodes we choose to merge. So let's first look at how to merge 2 nodes. Given we have 2 nodes, each has its own duty cycle and batch execution latency. We first use the minimum duty cycle of 2 nodes as the new duty cycle, and then we need to adjust the batch size and execution latency for each node. And then we just verify whether the occupancy of the merged node is greater than 1 or not. And in order to determine the merging order, we follow the same heuristic as the greedy algorithm used in for the bin packing problem. We first sort all nodes by its occupancy in decreasing order. And for each node, we first try to find a merging from already scheduled node that yields the highest occupancy. Otherwise, if we fail to find such a node, we directly add this node into the scheduled nodes. Next, I'm going to talk about how query analysis works. So let's first define the problem. The query analysis, given that we already know the query latency SO, the request rates for each model in the query, and then given a time budget, we know what's the maximum throughput a model can achieve on a GPU. And our goal is still minimize the total number of GPU for this query. So we first need to extract the data flow dependency graph between model invocation. And this figure shows an example of the data flow diagram for the traffic application. And we first use the SSD model to detect objects inside a frame. And then if it's a person, we then use a face recognition. If it's a car, we use a car recognition model. And second, we use dynamic programming to solve this problem. We define the function f as the minimum number of GPUs required to run the model U and its subtree given a time budget. For example, FST here indicates the minimum number of GPU we need for this query. And then to compute this function f, we split the latency budget T into two parts. The T prime is allocated for the root node. Here it says SD, and we compute the minimum number of GPUs for the root node. And second, we also accumulate the minimum number of GPUs for the subtree given the time budget T minus T prime. And we also iterate over all the different possibilities for splitting and then take the minimum as the output. And our final result is the f function given the root node and the query latency L. Okay, now let's talk about how Nexus batch across models. So Nexus computes the hash of subtrees of all models in the database and then detect common subtrees between two models by matching their hash. For example, these three models, they share the common prefix of 5 layers. Now during the runtime, the common prefix part is only loaded into memory once, and then different suffixes are loaded separately in order to save the memory for the GPU. And during the execution, after we get a batch of mixed requests to these models, we execute the common prefix in a batch and get the intermediate result. And then we execute the different suffixes sequentially. Now let's talk about the evaluation of Nexus. We compare mainly to the two state-of-art serving systems, the Clipper and the TensorFlow serving. And we mentioned that they both lack support of the class resource allocation and a complex query. So we built two baseline implementations for them. The batch oblivious scheduler allocates the number of GPU of a model proportional to its request rate and inversely proportional to the maximum throughput that this model can achieve under this latency SO on a single GPU. The naive query analysis simply splits the query latency SO evenly to each stage. And our first case study is the game analysis, inspired by those online streaming platforms such as Twitch and Mixer. We find that the passive viewers tend to pick the stream that are most interesting currently. So we built an automatic video analysis application for selecting the interesting video streams from many of them. And what's involved in the application is that we use the ResNet to recognize one character or one icon from the video stream, and I use the LaNet to recognize 6 digits to extract some game status. And some of popular video game can have thousands of streams, but there are also a lot of different games. So in this evaluation, we has total of 20 different games with the popularity distribution for their request rate. And we also specialize the ResNet for each game by fine-tuning the last layer. And we evaluate this application on 1610 Ti GPU with the latency SO of 50 milliseconds. This figure shows the highest throughput that these three systems can achieve while like 99% of requests are served within the latency SO. And we can see Nexus can achieve 9.4x higher throughput than the Clipper. And also to further understand what each optimization can contribute to the throughput, to the higher throughput, we then incrementally disable one feature at a time. First, we disable the prefix batching, and we can see that the throughput dropped by 12%. And then we replace the squishy bin packing algorithm by the batch oblivious scheduler, and then we can see another further 31% loss of the throughput. And because there's no dependency between two models in this application, so there's no complex query used in this application. And also there are further optimization we used in the Nexus that can account for this remaining differences between Nexus and the baseline. So you can refer to the paper for more details. And our second case study is the traffic monitoring. As we already explained what the application does, we're trying to recognize persons and cars in the traffic camera videos. So we also evaluate this application on 16 GPUs with the latency SO for the entire query of 400 milliseconds. And we can see the Nexus can still achieve highest throughput. And in particular, we can achieve 1.8x higher throughput than Clipper. And the query analysis can contribute for 90% of the improvement, and the squishy bin packing can contribute for 22%. And last, we evaluate the Nexus on a large scale on 100 KD GPUs and run 7 different applications with changing workload. And we can see the Nexus can adapt the GPU allocations based on the current workload, and we can serve requests mostly within the latency SOs. To conclude this talk, the Nexus serves multiple applications at high utilization on a GPU cluster and while satisfying the latency SOs. And Nexus uses squishy bin packing to schedule DNN workloads and analyze complex query and enables prefix batching across models. And our code is available at the following links. And now, thank you, and I can now take questions.
Hi, great talk. Petros Magnetis, Google Research. So I was wondering, the assumptions behind the utility of this work, which is great, is that you have all these opportunities for combination, right? For combining multiple models in the same GPU, or sharing prefixes of a model with multiple tasks. But as things are evolving and new models come out, these tend to become less prevalent. So models become bigger. So the more successful models are bigger. There's no opportunity for sharing weights from multiple models in the same GPU, or certainly for the fine-tuning examples that you gave. Accuracy is usually much higher if you let the model below the particular application fine-tune to the application. So you don't share weights there either. Do you see opportunities as you're moving to more complex, bigger models for your approach to work? Will it scale to multi-GPU situations where you might want to share, I don't know, in the Google TPU world pod across multiple applications? Or is it only applicable to single GPU kind of units?
Okay, so I think I can break down this question into two. So first one is the model getting larger, so can actually allocate multiple models on the same GPU? So actually, in fact, yeah, I agree the model is getting larger, but you can also see there's another trend of research trying to compressing these models into smaller ones. And then we can also see a trend that those hardwares are getting more and more powerful, which we can do more and more works at the same time. So I still can see there's a possibility in the future that we need to pack these models into the same hardware or accelerators. And the second,
for mobile devices maybe, but for data centers, I don't know. Is that a trend? I don't know. Maybe I'm missing something.
Yeah, it depends. For example, if we can compress the model while for 10x, and then you still achieve similar accuracy, I see people will still do that.
True.
Okay, and the second question is whether the fine-tuning still will applicable in the future as model, people train their specialized model for each application. I think it depends. For example, for different games, you want trying to get the best results, you can retrain the entire model. But if you can think of a business which you can serve tons of different games, and then you can, by fine-tuning only the last few layers, you can still get a comparable accuracy, but you can save tons of you can increase a lot of the efficiency on your backend. I think there's still a motivation you can do that. I think it's still still depends on how you train your models.
Thank you.
Time for one quick question, maybe.
Hi. Can you elaborate a little more about how much transparency into the models and the application specification do you need to make this work? Could I just give you a container and you could somehow prefix batch with another container that someone else gives you?
I think that's, so in Nexus, we need to ask user to use our API to develop their applications, and they need to upload the model weights to the database for us to analyze. If you only give a Docker container which hides everything of your application, then we are not able to support the prefix batching of some other things.
All right, thank you.
All right, let's thank the speaker again.